Now the next part, which is Jordan measure and Jordan measurable sets in RD. So we have defined an elementary measure for elementary sets in RD. Now we would like to increase our collection of sets where we can define our measure. One choice, recall that if E is elementary in RD, then we had this formula ME was the limit as n goes to infinity 1 over n to the power d, the count of the set E intersection with z to the power d over n, where z to the power d over n was the set n1 by n, n2 by n, nd by n, such that n1, n2 up to nd is a d-tuple of integers. So we know this formula, and now one could try to define for an arbitrary bounded subset, E of RD, M of E. Now this is the definition. Remember that our definition of ME was via disjoint boxes, and you took the sum of the measure of these boxes, but we proved that this is equal to this limit. This is some kind of counting, but by normalizing it by a relevant factor n to the power d, we get a formula which gives you ME, the elementary measure of E. But now I am going to define this measure for any arbitrary bounded subset E to be by this formula, by this limiting formula. So this is our naive guess, because for any arbitrary bounded subset we don't have an immediate volume formula by just taking the product of sides of the intervals. So we can try to define it using this limit formula. So, but now notice that if E is the subset of rationals inside the interval 0, 1, then the measure of E via this formula is simply going to be 1. So for this is for d equal to 1 now, and so we have this interval 0 to 1, and for any fixed n you are dividing this interval into chunks of length 1 by n, and so these points 1 over n, 2 over n up to n minus 1 over n belong to this set E intersection z over n, and so we will have how many points? 1, 2 up to n minus 1, but you will also have to consider these 2 points. So you will have in total n plus 1 points, and then you divide by n, so you will just have 1 plus 1 over n, and when you take the limit as n goes to infinity you will just get 1. So we will have the measure of this set E, which is the rationals in 0, 1, is simply 1, but if y is an irrational number, so let's say y equals square root of 5, then if you translate this set E by square root of 5, then the measure of this set is 0, because this set E plus square root of 5 intersection z by n is empty for any n, because E, remember, is made up of rationals in 0, 1. So if I take Q, a rational, let's say P by Q in 0, 1, and you have P by Q plus root 5 is some k over n, then this implies that root 5 is a rational k over n minus P by Q. This belongs to the rational. This is a contradiction. Therefore, this set is empty. This set is empty for any n, and so the count is 0, and so in the limit you will get 0. Therefore, if we try to define our measure E for an arbitrary subset using the limit formula, then this fails the translation invariance property. So if you take the if you take the limit formula, fails the translation invariance. Therefore, since we want our measures to satisfy finite additivity and translation invariance and non-negativity, we will try to approximate any arbitrary set in RD by elementary sets, and see whether by approximations we can achieve some reasonable results. So to illustrate this approximation, here we have a picture of an arbitrary subset E. So this is an arbitrary subset of R2, and it is definitely not a box or an elementary set. So this is not an elementary set. So the idea here is to look at boxes which are lying completely inside E and take the union. So you will have, so the union of all these colored boxes is an elementary subset which is lying entirely inside E, and if we increase the number of such boxes, it's quite plausible that E can be approximated from inside with elementary sets. This is the union of boxes. So here, for example, here you can have another box, here you have another box, and so on. So all these gaps can be filled with more boxes, and you can have a nice approximation of E using entirely elementary sets. Similarly, you can have an approximation of this set E using elementary sets which completely cover E. So here E is a subset of the union of these colored boxes Bi. So these are the boxes Bi, and if E can be covered by such boxes, then and E can be approximated from outside by these boxes, then we can hope to use our already well-defined notion of elementary measure both from inside and outside to create a new measure for arbitrary subsets of RD. So let's see how this is done. So this is the inner and outer Jordan measure. So suppose that E is a bounded subset of RD, which need not be an elementary set, it's just bounded. So we define, so this is a definition, we define the inner Jordan measure of E as, so we will denote the inner Jordan measure with a lower subscript j. We will denote it like this. This is the inner Jordan measure, and by definition this is the supremum over all elementary sets A inside E, A elementary, of the measures, elementary measures of A, elementary measure of A. So you are choosing an elementary set A which lies completely inside E. You are taking the measure of that set A, and you will take a supremum of all such elementary sets, and this numbers m of those the elementary measures of those sets. Similarly, the outer measure, outer Jordan measure of E is defined as, now we will denote it as m with a superscript j, and this is defined as the infimum over E subset of A elementary MA. So in the first one we will approximate from inside, this is approximation from inside, and the second one is approximation from outside. Now we can define what is a Jordan measurable set of RD, Jordan measurable sets. So this is a definition. So a set E, a bounded set E, a subset of RD, is called Jordan measurable if we have the equality of the inner Jordan measure of E with the outer Jordan measure of E. Note that because we have chosen E to be bounded, since, so this is an important remark, since E is bounded, there exists an elementary set, A of RD, which completely covers E. So here we have some E, then one can always cover AE, this set E, with an elementary set or even a box. We can even take a box. There exists a box A such that E is completely inside A. Therefore, the inner Jordan measure, which is the supremum, by definition, the supremum of these sets A elementary. So let me write here B elementary of MB. Now we know that here we have all these B's sitting inside E totally. Therefore, by monotonicity property, we have M of B is less than or equal to M of A for any elementary set E, elementary set B sitting inside E. So therefore, if you take the supremum over all such B elementary, then this is still less than or equal to M of A, and this is nothing but the inner Jordan measure of E. Therefore, the inner Jordan measure, this implies that inner Jordan measure is always finite. Always finite. Similarly, one can have the outer Jordan measure will also be always be finite, because so similarly outer Jordan measure will also be a finite number for any bounded set, E. This is because the outer Jordan measure of E is by definition the infimum over all sets B which contain E, and all these B's are all elementary, and you are taking the measure of these sets B. But note that since E is bounded, there exists a box, now let me call it A, which contains E. As we saw before, there is always a big enough box because E is bounded. Big enough box which contains E. So this box A is now admissible in this collection of elementary sets which contain E. Therefore, this is always less than or equal to M of A, which is finite. Therefore, we see that both inner and outer Jordan measures are always finite, and by definition we'll have that set will be called Jordan measurable if these two finite numbers agree, which means that the inner Jordan measure is equal to the outer Jordan measure. So in the next lecture we will see more properties of Jordan measures, outer Jordan measures, inner Jordan measures, and will give conditions, necessary and sufficient conditions for the Jordan measurability of a bounded subset of RD.